Welcome to today's webinar. I'm Matt Sederberg, a co-founder and CEO at Coreform. Greg Vernon is Director of Product Management at Coreform. Dr. Michael Scott, Coreform co-founder and president, will also be on the line helping to answer questions. As most of you know, the drill on these webinars, we will be recording this, but throughout the webinar, we welcome interactions with you. You can chat with us. It's a little bit more effective if you use the Q&A. That way your questions can go in the queue, and we'll respond to them either live or in real time. So with that, I'll turn the time over to Greg.
All right, thanks, Matt. And thanks everyone for joining us today. We're really excited to share with you the latest progress we've made with Coreform IGA. So just a little bit, from an agenda standpoint, we'll introduce Coreform, if you're not familiar with us, and then also kind of a short introduction to Coreform IGA, the software tool that we're developing. And then we'll dive into a demo of using Coreform IGA to solve a problem that deals with predicting failure. And including a live demonstration of the workflows that we're building. And then we'll have some time for Q&A at the end. So without further ado, just go dive in. So Coreform was founded in 2016 and has now grown considerably. In fact, last year, Coreform was recognized as the fastest growing simulation company on the Inc. 5000. And this is a bit of a dated photo because it's pre-COVID of the Coreform team. And we've grown since this photo. So hopefully once COVID is finished and we're able to get back together, we can take a new family picture. As Matt mentioned, we are recording this webinar, and we do record all of our webinars and we upload them to our YouTube channel. And so I'd encourage for you all to subscribe to our YouTube channel to be notified when this webinar is posted or when our other webinars are posted if you're unable to attend. And so as you can see, our YouTube channel, you can either search for Coreform or you can put in our Coreform LLC channel. And now I'm going to talk about Coreform IGA, but before we dive into this, I'd like to ask Matt to start the poll that we have. So Matt, if you could bring up the poll. So really what I hope you get out of this webinar is that we are developing tools that can reduce your pre-processing time for mesh generation and model building of your simulations. So I'd like to just ask and get kind of a query of the attendees: how much time are you spending pre-processing a typical simulation or your project for your simulation? And so as you can see, I kind of have this by half a day, maybe a half day to a day to a week, and kind of so on. Yeah, so if you don't mind, we'll give us about 20 more seconds to let people respond. And then Matt, I don't know if people are able to see the polls or not, but thanks everyone for getting your votes in. So maybe we'll give us about 10 more seconds. Oh, there we go. Perfect. All right, so I don't know. I presume that everyone can see. So it looks like we've got quite a few people who spend around a day to a week of business hours pre-processing simulations. So hopefully for these folks, can show how you can use Coreform IGA to accelerate your pre-processing time and accelerate your design cycles. All right. So really the big question in the area that Coreform is trying to fill, we really need to talk about why Coreform IGA? What problem are we trying to solve? So this is a diagram of a workflow that was studied and analyzed by Sandia National Labs in the 2000s. that looked at, in a typical simulation workflow at Sandia, how much time were their analysts spending at different parts of the simulation cycle. And as you can see, spent a lot of time in these non-value added areas. They're taking a design model and then de-featuring it to make an analysis solid model. Or in order to prepare it for hex meshing, having to decompose the geometry. And then the actual process of trying to build a hex mesh and iterating on that. And then making sure it's a quality mesh. So these portions of the pre-processing workflow really aren't value added. They're just time spent trying to get a simulation ready to go. And IGA and Coreform IGA in particular, our motivation is to drive those portions of the workflow to effectively zero. And let the analysts decide, really have full control over how much time they actually spend in those parts. And one way, the biggest way we can do that is by decreasing the overall meshing time and relaxing the constraints that lead to those expenditures in meshing and pre-processing. We can do this largely due to technology Coreform developed that allows us to increase your simulation accuracy through spline basis functions. And then if you put all these things together, the real business value or goal is that you can then radically accelerate your product design process. And so really Coreform IGA is about, it's a business tool. And if we look at where it fits within the realm of simulation tools, we can kind of categorize solver technologies as being, from an overall time to solution, as being either slower or faster, and then their accuracy from either low accuracy or high accuracy. And there's value to having low accuracy in the early stage design cycles. There's also still value in having high accuracy. And if you look at the traditional finite element approaches, hex-based FEA versus TET-based FEA, hex-based FEA is more accurate typically than TET-based FEA, but it does require more time to get to a solution due to the manual labor required to build hex meshes. And then TET-based FEA is faster overall, but it is maybe computationally more expensive. So it isn't as fast to go. But you also then you give up some accuracy. We've seen recently now more methods being developed, like mesh methods and voxel-based methods, that sacrifice accuracy in the name of more speed. Now, Coreform IGA is developing a Coreform IGA tool with these higher order smooth basis functions, which allow it to have even higher accuracy. And with traditional body-fitted U-splines, which is our patent-pending spline technology, we can either take hex-based FEA and make it more accurate and faster to solve, or we've now developed these immersed spline technologies, which allow us to have the speed of mesh methods, but with the accuracy of hex-based FEA, or improved, in fact. And so this is kind of the spectrum or the location where Coreform IGA is designed to live in. So highly accurate solutions that cover the entire spectrum from a lot of model prep time for the most accurate solutions to fast solutions with their immersed splines. And so I want to dig in a little bit into this spectrum. So if we just lay this spectrum down from traditional finite element approaches on the left, which typically have more manual labor involved, but do typically result in some faster solves for top nonlinear problems, and then traditional immersed, where you have less manual labor, but maybe the solves are more computationally expensive. So as you can see on the left, traditional FEA with hexes, you would do manual labor to say defeature. So we'll see that there are some fillets that defeatured here, but then decompose to put on a hex mesh. Traditional immersed methods just fully immerse the geometry without defeaturing. So here we can now see these complex fillets and chamfers. And now we're going to rely on the computer doing some adaptivity and doing more work to get out accuracy. What we've found and developed is the ability to say, identify the regions that are difficult to mesh, and only in those regions we can relax the requirement to be body fitted, but still be largely body fitted in most areas. Or even if an analyst chooses, we can only fit just the major features of this geometry. So in this case, fitting the symmetry planes, the top and bottom surfaces, and the outer radius. And then from here, allowing the computer to then adapt to get out the solution. And so really, what we've done now is the analyst has the ability to choose for each component in their model what level of accuracy and computational expense they need to get out their solution. So it's full flexibility provided to the user. If we look at that second from the left, I just want to show the detail here where we are body fitted on most of this geometry. But as you can see, what makes this geometry difficult, if not almost impossible to hex mesh without defeaturing, are these fillets, especially these complex fillets on the shoulders. So what we've done is we just relaxed the requirement of body fitting in those local regions, and then we'll use the local adaptivity properties of our U-spline technology to then drive accuracy to whatever level the analyst requires. And so, as you can see, with this approach, isogeometric analysis, we've now got this tight CAD connection to the geometry, the design geometry. We've got a greater accuracy per degree of freedom due to our use of our spline basis functions, but also the ability to have partially body fitted meshes that then are relaxed and immersing just certain regions. And this results in a more efficient compute. And overall, we've now calibrated or allowed the user to calibrate the speed and accuracy, make the trade-off that they need for their problems. Now, Coreform IGA is built on decades of research in finite elements and isogeometric analysis. It is still under development, but we're making great progress. And so what I'm going to show you today is the latest updates we've done to Coreform IGA with our strategic partners. But I wanted to give you some insight to the current capabilities of Coreform IGA, but also a bit of the vision. So Coreform IGA is a native implementation of IGA, taking these decades of research and putting it into a native solver. We support both linear and nonlinear solvers, static and dynamic physics, using both implicit and explicit time integration techniques. We support nonlinear materials, geometry, contact, and more nonlinearities are coming. Some of maybe the mechanical engineers in the world who have nightmares about Fortran might be happy to hear that our user materials and user subroutines are implemented in Julia. And then currently our input files are encoded in JSON, which is a human readable format and is highly structured. So I'd like to, just before we dive into now our demonstration of using Coreform IGA to predict failure, I'd like to maybe take a moment to just see if there are any questions about what I've talked about so far. Matt, are there any questions in the queue?
You can go ahead, Greg.
Right. So this is the problem we're going to be looking at today comes from textbook, actually my undergraduate textbook. This is something that when I first started getting into finite elements, that I found that I used, and I recommend this for other folks who are maybe new to finite elements, that I used my undergraduate textbooks and techniques that I was familiar with to really test to make sure that I knew how to apply finite elements in the right way. And so undergraduate textbooks typically you're able to have hand calculations. They're amenable to hand calculations. And then it allows you to then test and verify against your finite element solution. And so this was actually one of the first problems I ran when I was a new engineer with finite elements, just to make sure that I was understanding. So this is a 1.5 ton hydraulic press for removing and reinstalling bearings in small to medium-sized electric motors. And there would be a hydraulic cylinder mounted vertically within the C-frame. And the C-frame was proposed that this would be a gray cast iron. So one of these you can see here is that on the right, I've got maybe how this might actually look from a design CAD model. That the schematic here, we haven't really captured fillets, but in practice, we're gonna want to round off sharp edges from a hazards perspective. We want fillets so that we don't have stress concentrations and crack propagation. So this is something to keep in mind, that the CAD geometry for this schematic looks a little bit different. And so, as I mentioned, we're using the great cast iron here, which has an ultimate tensile strength of 50,000 psi. And I apologize to our metric friends out there that I'll be using an English system for this analysis. Maybe someday we can all get onto metric for everything. But for today, we'll be showing this in English. Now, gray cast iron follows a brittle material failure. And so I don't have to remind everyone about this, but just go through this here, that if you recall, brittle materials typically don't have a lot of plastic strain before they fail. So the ultimate stress typically equivalent to the fracture stress, and that's usually very shortly after the yield. And if you look at like a max normal stress theory, we do see that cast iron does follow this model of whenever the maximum tensile stress, normal stress, exceeds the ultimate stress value that we have failure. And so we're going to go ahead and use the maximum principal stress here as our criteria for failure. And again, as I mentioned, this is a good practice for you to do, for any engineer to do when they're doing final element, is to do hand calculations. So as you can see here, this is how, even if you've been provided that geometry with fillets, you'd still probably idealize it down to this simplified geometry of two rectangular sections. And then we can compute out the maximum stress at this inferior point through a curved beam bending equations. We get 127.2 ASI, 1,000 PSI. And of course, based on our previous assumption of gray cast iron, that maximum tensile stress is larger than ultimate tensile stress, and so we would predict failure. In fact, we predict failure by quite a bit. Now, so we make this is a bit of a contrived problem, but if we look at a traditional finite element approach to pre-processing this model, where it's hex-based, this is representative of the pre-processing that one would do, where we start off by defeaturing fillets, the small features that don't matter, and then we decompose our geometry into hex meshable blocks. We can then put on a nice high quality hex mesh. And then we'll be looking for stress on this internal surface. Now, again, this is a simple model, but from complex models, this process, again, as Sandia's analysis showed, can take upwards of 80% of the overall time of a solution. And even with tetrahedral mesh generation, if you don't do defeaturing and you desire a coarse mesh, you can oftentimes have these poor quality tetrahedral elements, which might be fine for a linear static analysis, but for nonlinear analyses can result in poor convergence as well as poor results. But if you don't want to defeature, but want a quality mesh, then you have quite large finite element meshes in order to capture the small features in your geometry as well as the large features in your geometry. Now, Coreform IGA, what we've done instead, if we recall back to that spectrum we talked about earlier, we can take the CAD model as is without defeaturing, build the mesh or a computational domain that envelops that geometry, and maybe in this case follows the overall features or characteristics of this model. So we can kind of approximate this as like a horseshoe that's like an extruded square that follows like this shape. And so now if we look at this, we've now partially immersed part of our model and then our body fitted on some other surfaces. And then as a quick note, one of the things you'll see throughout here is, as I mentioned, Coreform IGA is still under development, and we'll be looking at quadrature points. So when we have cells that have been cut by the geometry, we'll be using an adaptive quadrature on those regions. But you'll see these spheres in some of the results today. And what those are is those are the quadrature points being shown directly as a result. So as you can see here with the linear Gauss quadrature, but then also with cubics, you'll see even maybe finer meshes of points. So I just wanted to orient you that you'll see a lot of points in some of the results we'll have today, but it's not points in the same way as like a mesh method, like an SPH or a material point method. They're just the quadrature points, not actual particles. All right, so now what I'd like to do is switch over to a live demo. If there are any questions now, though, this would be a good time, Matt, for us to answer some of those while I switch over.
Yeah, go on ahead, Greg.
Okay. All right. So one of the other products that Coreform has is called Coreform Qubit, which itself has a long legacy of being developed at CMB and national labs. It is a world-class text meshing software. And so what we can do here is we've imported our step geometry as is. And what we're going to do is we're actually going to define on the physical, this is going to be our physical domain of our problem. We're going to go ahead and specify load surfaces on this physical geometry, not on the mesh. So what I'm going to do now is create some load surfaces. So to do this, I'm going to split these surfaces. Actually, first, let's do split these curves. I'm just going to split the curves on this upper surface. So that we have a region so you can see here now I've split this curve. Draw vertex for our vertices are visible. So you can see I've now added a few vertices, and I'm going to split this surface through those vertices. And so now I've got a surface in my physical domain with a CAD geometry that I can apply a pressure load to. I'm going to do the same on this bottom surface. And now what this means is that I could change the size of the surface if I wanted. I could have changed where this location was, but I won't actually have to remesh the mesh that we'll see that I'll create. So we've kind of dissociated needs of or impositions of how I'm defining my model and boundary conditions and load conditions, dissociated that from the mesh. So there's no longer this cycle of build the mesh, change the boundary condition, go back and remesh, change the boundary condition, go back and remesh. We've removed that part of the workflow. Now what I'm going to do is I'm going to start creating the geometry that's going to hold the mesh. And so I'm going to start by just simply creating a bounding box, a tight bounding box of this C frame. And I could build a mesh just directly on this geometry, and I'd be ready to go. I could send this off for a simulation. So this is part of like that spectrum. That this would have required almost no time. I mean, no time actually to create the mesh. I've only spent time just defining where I want loads and boundary conditions on my geometry. But if we want maybe a little bit more efficiency and accuracy per degree of freedom on these surfaces, where I had kind of intuited that I'm going to have interesting stuff, then I might want to have a slightly different geometry. So here what I'm going to do is I'm going to just cut this geometry by the interior and exterior surfaces. So I'm just going to select these interior surfaces of the C-frame. And I can preview what this cut is going to look like in blue. So it's going to trim away this internal region. Right, so now I've got two regions here. Now I'm going to delete this yellow volume. And now I'm going to trim away this kind of these these little regions on the outside here. So I'm going to do the same thing here. Select these surfaces. Make this cut. Again, we can preview this cut cubic. So you can see the little blue surface is showing me what the cut's going to do. And so now we can see the yellow volume here represents the domain, the computational domain, where I'm going to build my elements. Now, I could just build our use-plane mesh just directly on this yellow surface. Well, what I want to show is that this fits within Coreform IGA. Still even fits within like traditional FEA workflows, and it still even do things like do web cuts. So I'm actually going to make a web cut here, just to show that we can do this. So I'm just going to trim off these, make a cut on these rectangular prism sections. I'm just going to make this cut here, and then I can merge these volumes together for a conforming hex mesh on this. And then I can specify, say, element sizing in qubits. So I'm going to maybe say choose 0.5 for my element size. Give you what that mesh is going to look like. And then create a swept mesh on those volumes. So this is going to be the layout of my use-spline mesh, because we can see, so this is just showing us, the linear layout. That again immerses our computational domain, or sorry, our physical domain. And I can then build a use-spline. So this is a command that's coming into Coreform Qubit very soon. It's the ability to build use-splines. And I can specify degree and continuity. So maybe I want to build cubics that are maximally smooth and build that. Now, we can also then build a quadrature scheme. So I've already kind of built these. I want to show, let's maybe just draw these by solid color. So as we can see, as I mentioned, this is a cubic mesh. We can see then the adaptivity. You can see the outline of those hex elements that I built in the C-spline, and then the adaptive quadrature to then capture the geometry that's been cut. And one thing we haven't shown here today is the ability to then have further adaptivity of the elements to capture small features of the geometry we wanted. So we're just showing an unrefined or unadaptive mesh of it. But this is a mesh that I'll refer to later in the results section as the coarsest mesh that we ran with use-splines. But I just wanted to orient folks to what this looks like. And then we have another command that then actually constructs the quadrature scheme for this volume. And I can specify how many layers, how many levels of adaptivity for the quadrature do I want. So in this case, I could choose either one level of adaptivity, 2 levels, and I can save the cards. And then Coreform will go ahead and build that scheme for us that I've shown here. And we can then run this simulation in Coreform IGA, and we can extract out stresses, as well as you mentioned, this maximum principal stress. And as we can see here in this result that are plotted, so here I'm plotting the quadrature points by their maximum principal stress. We can see that we're right about that 130, 127 KSI maximum principal stress on this internal radius here. Right. So that's the live demo. Are there any questions about this live demo, the functionality that I've shown here so far before we actually get in and analyze the results. Any
Yeah,
questions, Matt?
yeah, we've got a few questions, Greg. So would the immersed method be able to be extrapolated to larger assemblies, such as the analyst wouldn't need to worry about meshing each individual component on an assembly, but envelope the entire assembly with a representative bounding box?
Yes, that's a very good question. So, and Mike can chime in on this, but what we would do for a large assembly is you would build a bounding box like this simplest bounding box that I built for regions that you don't care about. If it's not critical, right? So for a critical region, you probably want to have, if this was the critical component that if it failed meant that there would be loss of life or injury, we would probably want to have the mesh that we've shown so far, where it's at least largely body fitted. But for regions that you don't really care about as much, what we would do is we would build a unique volume for each one. It's still trivial, but it's not one single bounding box or one single domain, but a series of simple or trivial domains. And so you can imagine like this assembly would be built of many of these. So it's a very good question. Hopefully that answers your question.
So here's a kind of a similar question. Would the bounding box approach that you're showing have a faster solution time compared to hex meshing?
Yeah, so that we haven't yet been able to really compare in terms of total time. What I will say is that what's valuable with the approach that we've done here today is that when you take a geometry and when we defeature it, let me maybe draw volume 1 here, right? So this geometry is almost impossible to hex mesh. We might do a challenge at some point and offer a prize to whoever can build a fully conforming body fitted hex mesh on this volume. So again, the typical approach is to remove or defeature parts of this model. So here I might, this is probably an okay defeature, but even if I remove just that fillet, this fillet is even a challenge. And so you might even come to the point where you're removing these fillets. So from a convergence standpoint, you're no longer converging. You've like changed the problem definition by doing this defeaturing. And so to some extent, right, you're solving a different problem. But I would imagine that if you just look at like the total time, like the actual compute speed, the hexes might be faster in this case than the bounding box approach. They might be. But they're linear, and so to get the same level of accuracy, I would surmise that the bounding box approach would be much more efficient. And I've got some examples of the convergence rates for the horseshoe mesh. Maybe will help show why I'm making that. But we don't have a concrete answer yet for the bounding box approach. But by being able to use high order basis functions, I would imagine that for the same level of accuracy, the bounding box approach would be much more accurate and faster.
Thanks, Greg. So let's go one more question, then I'll let you push forward.
Okay.
This is from Eric. Can contact happen within a bounding box as well as between parts in different bounding boxes?
Yes. So we have, if we kind of think of like the bounding boxes like self-contact, so we can have, and again, Mike, you can feel free to correct me anywhere if I contribute a little bit here. We draw volume. So in this bounding box, if we had say compressed this, we could have contact between these interior surfaces. Those could come into contact with each other within this bounding box. We could also have contact if we say had two of these together and their own separate boxes, and maybe they're kind of like linking together. We could have contact between those parts of the assembly. So yeah, so both kind of approaches to how we would do contact do work. Yeah, and that's really the value behind this approach, is that we have to be able to support complex assemblies with contact in other dominant areas. So that's really a key requirement and key feature of Coreform IGA. Yeah, good, great question. Thanks for that. So if we now look at the results, so I've compared a traditional finite element solver. These color maps, by the way, are on the same scale. So they have this, both have the same color for 0 and the same color for the maximum stress for both of these. So they're at the exact same scale. Coreform IGA on the left, we're looking at, this is a cubic result. And we're looking at the maximum principal stress. You see that these have very good alignment in the results. However, this mesh, we'll see, is actually the finest mesh that we did for the traditional FEA. We'll see on the following slides. So I think there's something like the element count. There's just shy of 1 million elements in this solution on the right, and about 1,000 elements on the solution here on the left. So what I've done here, so these are just to look at the results, looking at the convergence to stress. Notice here that I've, just for guidance, I've put in where the hand calculation is at. Now, recall the hand calculation doesn't have a material assignment to it because it makes the assumption about no deformation. So we don't expect these to converge to the hand calculation, but the key is that they're in the ballpark. And so the fact that the hand calculation is closely aligned with our FEA results gives us confidence in our FEA results being correct. And then I've colored these different boxes by kind of trying to build roughly equivalent meshes between the traditional finite element approach here with the square boxes and the Coreform IGA results. So you can see I ran a very coarse mesh, that one that I showed at the very beginning of this with Coreform IGA, and it's almost as accurate as the finest traditional mesh, which I showed just previously. So this finest solution here is almost the same level of accuracy as that very coarse mesh that I showed here with IGA. And then what we're really managing, we're looking at like element counts here. But if we look at degrees of freedom, that's maybe even a bit of a clearer picture. Degrees of freedom are really how expensive is it for solvers to solve it. I think again, we can see that the same amount of degrees of freedom, we're much more accurate. And what that means is that we can have much fewer degrees of freedom. We get similar or same level of accuracy. So we can see here that we've got for a given number of degrees of freedom, we have like 1, 2, 3, almost 4 orders. Well, I guess not that order of magnitude. I guess we need to look next to the pi. You can see that for this same level of accuracy is 1, 2, almost 3 orders of magnitude fewer degrees of freedom to get the same level of accuracy. So 1,000 times fewer degrees of freedom, 1,000 times faster, roughly speaking. And that's really the value behind being able to have these high-order smooth basis functions. And again, as I mentioned, we could even use this alternative modeling approach where we use this tight bounding box instead, which now requires no time for the analyst to build the mesh. And then with this coarse mesh here, we also get good alignment. It's rounded up from like 1.42, so it was a little bit higher, but it's again in good alignment with the previous results. So that's without any adaptive elements or adaptive use line. We've only used this adaptive polisher on the space mesh. So even the tight bounding box approach can yield accurate solutions. I also wanted to show switching ductile material failure. So if we switch over to, like, say, a steel, like a 304 or 316, again, we can see that either Tresca or von Mises failure criteria is often used. And we have good agreement here. And so we'll use von Mises in the next results just to show the failure there. And again, we have this period where we have material begins to yield, continues to yield through an ultimate stress until it finally eventually fails due to some fraction criteria or something. So what I'm showing here is that we have this is a simulation we ran with perfect plasticity. And so that's why you see here that then the stress doesn't change when we have a perfectly plastic material. But what I want to show here is that Coreform IGA, even with this immersed mesh, can handle extremely large deformations and can converge easily to even these large deformations, large regions of plasticity in this solution. So I'll just pause this on the very last kind of frame here. So again, even with the reverse mesh, smooth splines, we've still been able to capture and converge well on this large mesh process. So of course we predicted the failure has occurred in this model. Failure based on that this part has yielded and is no longer serving its purpose. So I do want to make a couple comments here that, so of course, for this problem, we probably didn't need to use FEA for this specific problem. That's because again, this problem was from an undergraduate textbook. It was meant to be intuitive and easily adaptable to hand calculations. So really, this problem is more useful. The specific problem is more useful for verifying that you got a grasp on how to use FEA, how to apply it. But the real point is that FEA and Coreform IGA, those are necessary for many complex assemblies where it's not necessarily intuitive what your loading conditions are or how your geometry results in certain stresses. You might still be able to do a hand calc, but you may not even know how accurate your hand calculations are. So you're really using FEA or Coreform IGA to help give confidence even to what you might be doing with hand calcs. And then Coreform IGA for those complex assemblies can then simplify and thus accelerate your model building for those assemblies. And so, for instance, if we were, this is a model from GradCAD that I pulled, that if you had a complex assembly like this rotor, this helicopter rotor assembly, it may now not be quite obvious what a stress on this fillet might be, or what kinds of dynamic loads you're seeing in some of these members, and what the loading paths are. So this is where having an easy approach or simplified approach to building a mesh that still give high quality, high accuracy results is valuable. And so just to summarize, the real motivation for Coreform IGA is to accelerate your design cycles. This can speed up the development of your products and processes, shorten your time to market. And it does this by simplifying your model building. It also allows for more engineers to participate in performing these predictive simulations by being able to not having to be experts in building hex meshes. By simplifying model building, you can reduce your labor costs, which can allow you to either do more simulations for the same cost. So maybe you need to be able to solve more problems, more products, or do the same set of simulations but for less cost. It also eliminates geometric errors due to defeaturing, which is one of the primary sources of errors in finite element simulations. And it can do all of this while still yielding high accuracy results, but efficiently. So you don't have to have a supercomputer to solve these problems because we've reduced the amount of degrees of freedom that you need to get high accuracy results by orders of magnitude. And so let your compute resources work smarter, not harder. And so I'd like to encourage you all to participate in learning about Coreform IGA by going to our website and reading about it and reading our research results, going to our YouTube channel and watching our webinars. But also, if your organization is interested in becoming an early adopter of Coreform IGA, we'd like to have a discussion with you about where FEA maybe can't satisfy your current demands and how a strategic R&D partnership program that we have might help you help us understand your problems, and we can work together to develop solutions for your problems. And then also, feel free to participate in our public forum and ask any questions you have about Coreform IGA or Coreform Qubit or anything else at forum.coreform.com. So that, are there any questions? So maybe a lot. So
yeah.
Encourage tough questions.
Greg, thank you so much for the presentation. So here's a question from Shaquille. It's a good question. The horseshoe mesh does not look like the original model. For example, there's a concave notch that runs along it. How is that geometry captured in the swept horseshoe mesh?
Yeah, so let me see if I'm understanding this correctly. Are you talking about, you say concave notch? Um,
Yeah,
are
I think,
you
yeah,
are
I
you
think,
referring to like the spillet, like
yeah,
this?
I think the question is, I mean, that geometry is not the same as the coarse mesh you have. So how
Right.
do you
Yep.
capture the simulation?
Yeah. So the way that we capture this is that we have fictitious domains where there's no volume, and we have the real domain where there is volume, and then we're using our high order basis functions plus that adaptive quadrature to then accurately capture the fact that we've transitioned from a solid region to a fictitious region or a void. So that's how we're capturing this. If you are interested, our method is largely a generalization of the finite cell method, which is a finite element approach. So if you're interested in reading up about finite cell methods, that would be a good background for this. But that's really how we're capturing this, is by capturing it through having high order basis functions. You really can't do this without high order basis functions, so like cubics or quartics or higher, and this adaptive quadrature to then accurately integrate those functions in the physical domain. So that's how that's captured. Uh, it's one of the things I think is kind of funny that we always talk about, like, it's a finite element approach, but really the real workhorse of a finite element approach is really the basis functions. The basis functions are actually what are defining the solution. And so really what we just need to do is we just need to be able to integrate the basis functions in the physical domain. And we don't really care about the elements themselves. The elements are just a scaffolding to prescribe, a layout of basis functions and a layout for quadrature. But elements really aren't the first pass citizens in the finite element method. It's really the basis functions.
Thanks, Greg. Here's a question from David. Are thermal fluid solvers also under development for IGA?
Thermal solvers are. We don't yet have any customers who have been working with us on fluid solvers, but we certainly could build a fluid solver as well. But currently, our primary focus is on structural mechanics problems. Yeah, good question. So yeah, so I guess like the things like solid mechanics, contact, coupled with thermal mechanical as well. Those are kind of currently our core base of physics, but we do intend to expand our physics capabilities as customers have needed them. Good question.
Good. Well, Greg, thanks again for the webinar, the presentation, all the work you put into that, and thanks everyone for coming. As you mentioned, this webinar will be posted on our YouTube channel, and you're welcome to check back on Coreform's website for future webinars. Our next webinar next month will be an introduction to Coreform Qubit, so you're welcome to go sign up for that as well, and as well as the other previously recorded webinars. So thanks again, everyone, for coming, and have a great rest of your day.
Thanks, everyone.